Okay, in example 20.6, we're going to do something with the joint efficiency. So a cylindrical steel gas storage tank has an inside diameter of 18 inches and a wall thickness of 3/8 of an inch. All joints are full-strength groove-welded butt joints. Assume a joint efficiency factor of 70% and calculate the safe internal gauge pressure if the allowable tensile stress for the steel is 12,000 psi. Check the applicability of the thin wall theory. Okay, so you're given a cylindrical steel pressure vessel, inside diameter 18 inches, thickness 3/8 of an inch. All joints are full strength. Our joint efficiency is 70%, and our allowable stress is 12,000 psi, and we are to find the safe internal gauge pressure. Okay. So the first thing I do is I check for the applicability of the thin wall. In this case, 0.375 is less than 1/10 of the internal radius. So yes, thin wall applies. And then we're going to use the modified equation 20.1 to put the joint efficiency in. Okay, so our circumferential stress equals the pressure times the inside diameter divided by 2 divided by the wall thicknesses divided by the joint efficiency. Okay, sorry about that. And then we're going to solve for P. And then we're going to plug our variables in, and what we end up with is 350 psi. Okay, so what happens here is the joint efficiency ends up being inserted into this modified equation 20.1. Okay, our last one talks about a standpipe. This has to do with the hydrostatic pressure. Calculate and select the required wall thickness of the bottom section of a 15-foot diameter cylindrical steel standpipe that's subjected to an 80-foot head of water. Assume that the top of the standpipe is open. The allowable tensile stress for the steel plate wall of the standpipe is 12,600 psi. The plates are connected by a full-strength butt weld of 100% efficiency. Add approximately 1/8 inch to the computed wall thickness to compensate for corrosion and localized stresses at the junction of the vertical walls, and the bottom may be neglected. Okay, so what are we given? We're given a cylindrical steel standpipe. We have pressure head of 80 feet acting at the bottom. Our allowable stress is 12,600 psi. Our joint efficiency is 100%. We need to add 1/8 inch to the thickness for corrosion, and we're going to neglect localized stresses, and our diameter is 15 feet. Now, given all of that, select the required wall thickness. Okay, since we're selecting the required wall thickness here, we can't check for applicability until the end. And I don't think I did that. Okay. So, first thing we're going to do is we're going to find the pressure at the bottom. And that's this equation we gave you here. P equals 0.433 times H, where P is in PSI and H is in feet of water. So therefore, our pressure at the bottom of the standpipe is going to be 34.6 psi. Now, there's an open top, so therefore we're not going to develop any longitudinal stress in this standpipe. So now we're going to use equation 20.2 to solve for the required thickness, in which case we get 0.247 inches. We're going to add 1/8 inch for corrosion resistance. That's 0.372 inch, and then therefore we're going to select our plate as being 3/8 of an inch. Okay, that is it for lesson 10.